Guys, I'm in trouble. I really need your help. My girlfriend's home coordinates used to be 3, 8, 4, but she suddenly moved out, leaving behind a single strange clue. Rotate my position 60 degrees around the x-axis, then 30 degrees around the y-axis, and finally 45 degrees around the z-axis. Come, find me. Our mission is clear. We need to compute her new coordinates after these 3 rotations. This is a classic problem in 3D rotational motion. The cleanest and most reliable way to solve it is with quaternions. But without using quaternions, we can also solve using rotation matrices. The center of rotation is the origin. We take the point P and apply 3 rotations in sequence. Each axis has its own rotation matrix. Here's the rotation matrix for 60 degrees around the x-axis. Then the matrix for 30 degrees around the y-axis. And finally, the matrix for 45 degrees around the z-axis. To get the final transformation, we multiply these matrices in this exact order. In 3D, the order of rotations matters a lot. Rotating around x, then y, gives a different result than rotating around y, then x. Perform the multiplications. This gives us the combined rotation matrix. Now, substitute the coordinates of P into this matrix. The result is the new point P', the location where my girlfriend now lives. As you can see, this approach is long, tedious, and prone to mistakes. You have to perform 3 separate rotations and multiple matrix operations, so even tiny mistakes easily snowball. This is exactly why we turn to quaternions. With quaternions, 3 separate rotations compress into a single clean rotation. We only need 2 things: the axis of rotation and the angle of rotation. This is the axis around which point P rotates. This is the angle by which it rotates. Imagine the plane perpendicular to that axis and passing through point P. It's the plane of rotation. Within this plane, point P simply rotates by the angle of rotation. The center of this rotation is the intersection of the axis and their plane. What looked like 3 separate rotations reduces to one unified rotation. This follows from Rodriguez's axis angle theorem, which guarantees that any sequence of 3D rotations can always be represented as a single rotation about a unique axis. In this problem, the rotation axis is the line connecting the origin and this point. The rotation angle is about 90 degrees. It is equivalent to rotating point P around the axis by 90 degrees. Now, let's find my girlfriend's new coordinates using quaternions. This is the general form of a quaternion. The point P is expressed as a pure quaternion, 3i plus 8j plus 4k. The real part is 0. Next, we construct the rotation quaternion that represents the combined 3D rotations. The formula is Q total equals QZ times QY times QX. These are the rotation quaternions for each axis. Although quaternion multiplication is written left to right, the rightmost rotation happens first. Since we rotated 60 degrees around the x-axis, according to the formula, Qx becomes this. 30 degrees around the y-axis, Qy becomes this. 45 degrees around the z-axis, Qz becomes this. Pay close attention to these parts of the formulas. The angle that appears is not theta itself, but theta over 2. We multiply 3 quaternions in this order. You should perform this multiplication first. To perform this multiplication, we need to apply the Quaternion multiplication rules. Pay attention that ij doesn't equal ji. The order matters. Applying these rules, this is the Q total. The transformed point P' is obtained by this formula. This is the Quaternion conjugate, where all imaginary parts have opposite signs. Since Q total is this, the Quaternion conjugate is this. Perform the calculation in order. This gives us the new coordinates of P', my girlfriend's new address. It matches the value obtained through the rotation matrix method. Now, let's find the rotation angle and rotation axis. We obtain these from the fully composed rotation quaternion, Q total. The rotation angle theta is theta equals to arc cosine W. W is the real part of Q total. Applying the formula, theta becomes approximately 90 degrees. The formula for the rotation axis is this. X, Y, and Z are the imaginary parts of Q total. Compute according to the formula. This is the rotation axis, the unique line that stays fixed under the entire 3D motion. 3 rotations have truly collapsed into one. Compared to rotation matrices, Quaternions reduce the computational load and greatly minimize numerical errors. This is exactly why Quaternions are so useful for representing 3D rotations, and they are widely known to solve a notorious issue in 3D graphics and robotics, Gimbal Lock. Thank you for watching. In the next video, we'll explore why 4-dimensional Quaternions are the perfect tool for 3D rotation, so make sure to subscribe.